To summarize the last few weeks of phase equilibria, we've learned that the modified Raoult's law is good for modeling a system in vapor-liquid equilibrium where the components form a non-ideal liquid mixture, but the pressure is low enough to assume an ideal vapor phase. Most of the last week was centered upon finding a good model for these activity coefficients, gamma i's. So we talked about multiple different models for the gammas. Remember that these can be empirical or theoretical. If you don't know, empirical is a fancy word for experimentally defined. So you could do an experiment and you could obtain what the gammas are that way, and then you could fit parameters to models that describe these. Or you could do a theoretical or predictive model, in which you take pure component properties, such as the molar volume, etc., and you can use a modeling approach that predicts these gamma coefficients just based on what the pure components are. Remember that there's pitfalls and benefits to both. So in the empirical method, you have to run an experiment, but those tend to be a little bit more accurate because you can verify them and because the fit comes from actual data. While the theoretical is beneficial because you don't have to do any experiments and therefore you can obtain an estimate faster, but it tends to be a little bit less accurate. Today, we're going to move into Chapter 12 in the Dahm and Visco textbook, or Chapter 10.3 in the Sandler textbook, which covers what to do if your vapor phase is non-ideal, or what if pressure is high, leading to a non-ideal liquid phase, non-ideal vapor phase, I'm sorry. So to answer that question, I'd like to go back a little bit and start again with our equilibria criteria for mixtures. Recall that in a mixture, the equilibrium criteria is equal chemical potential, or another way that I can write that is equivalent mixture fugacities. So I can write FIV mixture is FIL for the mixture. And recall that this is equivalent to the same as mu I vapor equals mu I liquid. And next, recall the expressions that compose the mixture fugacities. So in the section that I talked about the Lewis-Randall rule, this is in class 17. From class 17, I've got the mixture fugacity of the vapor of component I is equal to yi times the pressure times the mixture fugacity coefficient. Go back and double check your notes. I'm not sure I had this hat in there, but I was supposed to. So this hat, double check. This is correct. I'm not sure if it was correct in lecture 17. Similarly, for the vapor, or for the liquid, I'm sorry, I think I had another mistake in the F hat I for the liquid phase. I did have a hat here, but I should not have. So this is the general application of the Lewis-Randall rule. So I had a mixture fugacity here, but this is supposed to be the pure component fugacity times gamma I. So these are both for the general non-ideal case. Non-ideal. So just by plugging these two things into my equilibrium criteria, I can set the two things equal. But first, I want to express the fugacity of species I. This is the fugacity of species I in the liquid phase. Recall that we've got the Poynting correction by Poynting correction factor. Let me go back and double check my notes to see what class period I talked about this. This was from class number 10. So you go back and double check the derivation of this if you're interested. But by the Poynting correction, I've got the fugacity. And this is the fugacity of the liquid, it's just not generally written as such, is the saturation fugacity times the exponent of molar volume times P minus P sat, or P star. Remember, I go back and forth on my notation. I personally like P star a little bit better, but the textbook you may have P sat there. Sorry about that. I X'd out of my OneNote on accident on my tablet. Divided by RT. And then recall that the saturation fugacity, you can rewrite that because since phi I is equal to fugacity of species I divided by pressure, because I can say this, I can also say that phi I sat is equal to, hold on. So because of how I define the fugacity coefficient, I can rearrange this. And because I say that phi is equal to fugacity over pressure, I can also say that the saturation fugacity coefficient is equal to the saturation fugacity divided by saturation pressure of component I. And because everything else is set, I'm just going to go ahead and, sorry about this, change my notation to be consistent within this expression. And I also need a fugacity of I there. All right, so if I solve for f sat I and I plug back in, and then I plug that in for the Poynting correction and plug this fi back into this fi, I can obtain my one step before the modified Raoult's law. So this is how we got to modified Raoult's law. It's xi gamma I pi sat times phi I sat times the exponent of molar volume P minus P sat all over RT is equal to YI P times phi I, mixture phi I. Okay, so this is the general, like I said, one step before Raoult's law. And last chapter, when we said that for ideal gas, i.e. low pressure, we had the mixture fugacity canceled, so this phi goes away. This phi I sat goes away, and also this exponent V times P minus P sat over RT, this goes to 0 since P is approximately equal to P sat. So for the ideal case, this all canceled, and we are left with the modified Raoult's law. Modified Raoult's. However, like I said, in this chapter and in the next coming week, we're going to talk about what if the pressure is not low and I can't cancel all these terms. What do I do with the rest of these? All right, so let's start with this term, the mixture fugacity coefficient, phi I hat. How would we go about evaluating that for a mixture? So I'll give you the short version first, and then I'll go back and I'll do the derivation in the rest of the video. I want to start by making an analogy to something we talked about way back in class number 8. So from class 8, we had the fugacity coefficient of a pure component. Class number 8, pure component fugacity coefficient. Fugacity coefficient was, so this is directly from your notes from class number 8. This is how we calculated the pure component fugacity coefficient. Remember that we rarely use this equation. Remember, because most equations of state are written in terms of P, there's another version where you can rearrange this and say that it is or equal to the integral from P is equal to 0 to P is equal to P of Z minus 1 over P dP. We did practice using this form of the equation. But for the mixture fugacity coefficient, the final form is very analogous. So for a mixture fugacity, ln phi I hat is equal to 1 over RT. Again, I'm skipping the derivation right now. I'm going to go do it in a second. I'm just giving you the final form so that you have it. This is how where we'll get to when I do the derivation momentarily. Instead of the molar volume, it's the partial molar volume, V over bar I minus RT over P dP. All right, so as I said, I'm going to go through the derivation next, but in the interest of keeping the video short and minimizing the number of mistakes that I make, I'm going to pause and I'm going to write the entire derivation and write my usual parenthetical notes, and then I'm going to just read it to you, and I'm going to see how that works. Okay, so I'm just going to scroll slowly. You can pause and take notes as you wish. This will be the final, this will wrap up our first video for today.